Welcome to the Deep Dive. Today, we're digging into something maybe deceptively simple sounding, force measurement. Specifically, using load cells.
Right.
And the big word we're tackling is accuracy. What does that even mean when you say a load cell is accurate? Because it seems like it's not just one single number.
Oh, absolutely not. That's a really key point for anyone listening who's involved in, design or testing or maybe monitoring equipment. Understanding that accuracy isn't simple is, well, it's critical.
Correct.
It really comes down to figuring out what level of precision you actually need for your specific job. Because, not every task needs the absolute nth degree of exactness.
Right, different needs.
Exactly. And getting that wrong, that can lead to, expensive mistakes, or maybe you miss something important. Are you, say, designing a totally new product? Maybe something critical like a medical implant.
High stakes there.
Definitely. Or maybe you're stress testing an aerospace part, or, just keeping tabs on how some heavy machinery is holding up. And the type of force matters, too. Are you pulling something apart? That's tension. Or squashing it, compression. Or maybe even twisting it, like torque. All of that feeds into which load cell you pick.
And therefore, the accuracy you can expect.
Precisely.
Okay, so that's our mission for this deep dive. Then let's sort of unpack what really goes into load cell accuracy. We want to shine a light on some maybe surprising things that affect it.
Yeah, things people might not think about initially.
Right, and help you figure out how to approach precision for your own work. And we've got some pretty compelling examples later on that show why getting this detail right really, really matters.
They certainly do.
Okay, so let's start broad. You said accuracy isn't just one number, it's made up of several things. What are those key factors?
Okay, yeah. So when we talk about a load cell's, let's say, overall performance or accuracy, we're looking at a few distinct characteristics all working together. There's something called nonlinearity. Basically, how much does the sensor's output stray from a perfect straight line as you apply more force? Ideally, double the force, double the reading, right?
Makes sense.
But in reality, there's always a tiny curve, so that's nonlinearity.
Yeah.
Then you've got hysteresis.
Hysteresis. Yeah.
That's the difference in the reading you get for the exact same amount of force, depending on whether you reach that force by increasing it or decreasing it.
Like it remembers where it's been.
Kind of, yeah. A bit like a memory effect. Then there's creep.
Creep.
This is where the output signal slowly changes over time, even if the load you've applied is perfectly constant and the environment isn't changing.
Huh. Okay. That sounds tricky.
It can be. Temperature effects are huge, too. Temperature swings can really mess with the sensor's sensitivity if it's not designed for it.
Right. Materials expand and contract.
Exactly. Then there's off-axis loading. What happens if the force doesn't hit the load cell dead-on, perfectly in line?
Like hitting it from the side of it.
Yeah, or just off-center. That causes errors. And finally, repeatability, which is pretty straightforward. How well does the sensor give you the same reading every single time you apply the exact same force under the exact same conditions?
Okay, wow. So it's a whole collection of potential error sources.
It is. And understanding these different bits is really step one in choosing the right sensor for your job.
That makes perfect sense.
Yeah.
It's definitely not just grabbing one number off a spec sheet. You mentioned creep and off-axis loading. They sound like they could kind of quietly mess things up. Let's dig into those a bit more. Creep first. How does that distort the data in practice?
Well, creep is, it's subtle but persistent. Think of it like this. Imagine you hang a weight on a spring. You expect it to stretch a certain amount and just stay there, right?
Yeah.
But with creep, maybe over hours or even days, that spring just stretches a tiny, tiny bit more, even though the weight and everything else is exactly the same.
Oh, okay. A slow drift.
Exactly. That slow drift is creep. And if you're doing, say, a long-term monitoring project or a test that runs for days, that slow drift means your readings aren't truly stable, even when the force is. It can really affect the integrity of your results.
I can see that. And what about the side loading or eccentric loading?
Right. So most load cells are really carefully designed to measure force along one specific direction, usually straight through the center of the primary axis.
Makes sense.
But if the force comes in at an angle, or maybe it's pushing down but slightly off to one side, that's side loading or eccentric loading.
And the readings get skewed.
Definitely skewed. But it's worse than that, potentially. It doesn't just mess up your data. It can actually put weird stresses on the internal parts of the sensor, stresses it wasn't designed for.
Oh, so it could actually damage the load cell, shorten its life?
Absolutely. It can lead to fatigue and premature failure. So it's bad for data and bad for the hardware.
Wow. Okay, so it sounds like even if you buy the most accurate, most expensive sensor on the planet, if you don't apply the force correctly, it's kind of useless. Which brings us right to mounting, doesn't it? How you physically attach it must be critical.
Oh, incredibly critical, yes. You hit the nail on the head. A poorly designed mount, or even just slightly misaligning it during installation,
Yeah.
that can completely sabotage the accuracy you paid for.
All that precision just gone.
Gone. It's often something people don't put enough thought into, but it can have massive downstream effects. And it's not just the physical mounting.
What else?
The environment it's in. Environmental conditions play a huge role.
Like temperature, you mentioned that.
Yeah, temperature's a big one. Temperature swings can change the sensitivity of the sensing element itself, introducing errors. Even a 5 degrees Celsius change might cause a noticeable percentage shift in the reading on some sensors if they aren't properly compensated.
Okay, that's significant.
It can be. And humidity can be a factor too, especially over the long term. In some unprotected load cells, moisture ingress can cause drift or even corrosion inside.
So what's the advice there?
Talk to the load cell suppliers early, especially if you know your application is going into a tough environment.
Like really hot or cold or wet?
Exactly. Scorching heat, freezing cold, high humidity, maybe even fully submerged underwater. There are specialized load cells built for those exact things, high temp versions, submersible ones with extra overload protection.
So solutions exist, but you need to plan for it.
You absolutely need to plan for it. Don't treat the environment as an afterthought.
Okay, this is all painting a picture where accuracy isn't just about, getting nice clean data for a graph.
No, not at all.
It sounds like it's often fundamental to safety, to reliability, preventing things from going catastrophically wrong.
That's exactly right. It's often the bedrock. Let's connect it to some real-world stuff, because that really drives it home.
Yeah, let's hear those examples.
Okay, think about this. Heart stents. Tiny little mesh tubes that hold arteries open.
Life-saving devices.
Absolutely. We have customers who use our load cells to test these stents during development and manufacturing. Now, once that stent goes into a patient, it has to work, period, for potentially decades.
Wow, the pressure is immense.
Imagine if the forces involved in making or testing that stent weren't measured with extreme precision. A tiny error, a slight miscalculation in force, could have devastating consequences down the line.
So in cases like that, accuracy isn't just nice to have.
It's not optional, it's absolutely fundamental. It's literally about patient safety.
It's powerful. Any other examples?
Yeah, shifting gears completely, think big science, like the Giant Magellan Telescope being built down in Chile.
Okay, huge project.
Huge. We're talking mass, incredibly expensive mirrors meters across. They have to be held in shape with precisely controlled tension forces.
Right, to get those perfect images of space.
Exactly. Interface load cells are actually being used right now to measure the tension on the support systems for that mirror glass. Now think about the stakes. If those forces are wrong, if the mirror bends even a tiny bit too much,
It doesn't just bend, it shatters. We're talking millions of dollars, years of work, just gone, instantly.
Wow. Okay, so from life-saving medical tech to cutting-edge astronomy.
Yeah. These aren't theoretical concerns. Getting the force measurement right, with the right accuracy, it truly matters in these high-stakes worlds.
Okay, so for someone listening, maybe working on their own project, how do they navigate this? How do they make sure they get the accuracy they actually need? It sounds like the journey starts before you even look at load cell models.
It absolutely does. The spec sheet is not the first place to go. The most critical first step. Ask yourself some fundamental questions.
Like what?
We usually boil it down to three main ones. First, what specifically am I trying to measure here? Get really clear on the goal.
Okay, what's number 2?
Second, what forces are really involved? Not just how big they are, but which direction are they coming from? Are they constant or do they change? How fast? How often? Get the full picture of the forces at play.
Right, the dynamics of it. Exactly. And the third question, which ties back to the start, how much error can I actually live with for this specific application? What's good enough? What level of uncertainty is acceptable?
Because it's not always more accuracy is better, necessarily. It might be overkill.
Precisely. Sometimes chasing extreme accuracy you don't need just adds cost and complexity for no real benefit. So answer those 3 questions first. Get really clear answers.
Okay, got it. Measure what forces, how much error is okay.
Yep. Once you have that clarity, then you start digging into the load cell specs. You look at the nonlinearity, the hysteresis, the temperature specs we talked about. You think about calibration needs.
And maybe standard off-the-shelf isn't enough.
Sometimes, if your application is really unique or demanding, maybe you need a customized design. And that's where, again, talking to the experts helps.
Consulting with the engineers at the load cell companies.
Absolutely. People who live and breathe this stuff, they can look at your answers to those 3 questions and help guide you to the right sensor, whether it's standard or custom. It can save you a lot of headaches later.
That makes a lot of sense. Get expert advice early. Okay, so we've talked about selecting the right sensor, considering all these factors.
Yeah.
But it sounds like it's not just a set it and forget it kind of thing either.
Oh, definitely not. Achieving accuracy is one thing. Maintaining it over the life of the sensor or through thousands of test cycles, that's an ongoing process.
What does that involve?
Well, regular calibration is key. Sensors naturally drift a tiny bit over time in use, so periodic checks against a known standard are crucial to ensure it's still reading correctly.
Like tuning a musical instrument.
That's a great analogy, yeah. And proper maintenance, keeping it clean, checking connections, making sure the mounting hasn't shifted or loosened.
Back to mounting again.
Always back to mounting. It's fundamental. These ongoing practices, they're essential for that load cell to keep performing at its best, giving you reliable data, cycle after cycle, year after year.
So it's a whole life cycle approach.
It really is. Enforced measurement, precision. It isn't just that number on the spec sheet. It's really the foundation for everything else, for good design, for safe operation, for trustworthy results.
So wrapping this up then, the big takeaway from our deep dive today seems to be that accuracy in load cells is, well, it's complicated.
It is, in a good way.
Yeah. It's this interplay of all those factors we discussed, nonlinearity, creep, temperature, mounting, everything. It really demands careful thought right from the beginning of a project all the way through its operational life. And understanding those details, those nuances, is what ultimately ensures you get data you can trust. And in many situations, ensures safety and prevents failure.
Couldn't have said it better myself. It's about looking beyond the surface level.
Okay, so maybe a final thought for our listeners to chew on.
Sure. How about this? Thinking about accuracy in this very specific technical field, force measurement. How might that make you look differently at assumptions about precision and reliability in other parts of your life? Maybe you'll start noticing the hidden complexities behind things that seem simple on the surface. You know, questioning what reliable or accurate really means in different contexts.
That's interesting. Looking for the unseen factors everywhere.
Yeah, just something to ponder.